Hi everyone, welcome to another video of Talent Catalyst AI, where we specifically strive to give you targeted knowledge on artificial intelligence that will help you in your career ahead and guarantee you industry success. The topic for today's video is confusion matrices, its definition, and understanding the whole concept of confusion matrix. So let's delve right into it. So let's first define what is a confusion matrix. So confusion matrix is also known as a error matrix. It's basically a performance measurement of for a machine learning classification problem. So what this means is whenever there is a classification problem and there is an actual and a predicted value, the predicted is something that the model predicts based on the historical data that it has been fed. Comparing the actuals to the predicted is known as a confusion matrix. How confusion matrix helps us visualizing the things is that it gives us a table layout, a 4 quadrant layout comparing the actuals versus predicted. So many of you might be wondering why this particular matrix is called as confusion matrix and why not some other name. Why is that particular term confusion given to it? It's basically because it shows how the model is getting confused between different classes by comparing the actual class with the predicted ones. So the actual versus the predicted is not always the same. In most of the cases, there is a difference, and the confusion that arises due to that difference is why confusion matrix has been named accordingly. So let's now look at the visual representation of a confusion matrix and try to understand it. So as we discussed just now, that a confusion matrix is a visual representation of 4 quadrants, right? So here it is. There are 4 quadrants, namely true positive, false negative, false positives, and true negatives. They are basically divided based on the y-axis we have actual results, that is the historical actual results, and the predicted results on the y-axis, and comparing actual versus predicted, wherein each has two classes, gives it a 4 quadrant look, that is 2 cross 2, 2 on the x-axis and 2 on the y-axis. Now let's try to understand the exact meaning of these terminologies, that is true positive, false positives, true negatives, and false negatives. Let's start with the easier ones, that is true positives and true negatives. Let's take a scenario where the model needs to predict a fraud. So there are two classes, 0 and 1, 0 being a non-fraud and 1 being a fraud. So if the model predicted value is not fraud and the actual value is also a not fraud, then this becomes a true negative, because 0, that is a negative number, negative class, is there in both actual and predicted. That is, actual was also not fraud and the model has predicted it as not fraud, giving it a name of true negative. The predictions are true but inherently negative. And just on the opposite direction, if both the observations, the actual value is also a fraud and the model also predicted it as a fraud, that is a 1, it becomes a true positive, that is predictions and the actuals match. Now let's come into a bit more complex ones, that is false negatives and false positives. So let's discuss false negatives first. So suppose an observation is tagged as a fraud, actual value is fraud, and the model predicted it as a not fraud, right? That is, actual is 1, the model predicted it as 0. This is why the name comes as false negative. False negative means it is actually a positive but the model predicted it as falsely negative, hence the name false negative. On the contrary, false negative, false positive, let's see this. Let's say the actual value or the actual target of this particular observation was a not fraud, that is a class 0. But the model predicted it as a fraud, that is a class 1. What it means is it was actually a negative, that is a not fraud, but it was predicted as a positive, meaning this becomes a false positive. Now what we'll do is we'll take an extra step to further understand the concept of confusion matrices using a use case or a case study. The case study basically is we are trying to, hypothetically, we are trying to develop a machine learning model that classifies emails as either spam or a non-spam. Right? There are two classes, 0 and 1, 1 being spam and 0 being non-spam. 0 is a negative class, 1 is a positive class. Since there are only two classes, 0 and 1, spam and non-spam, or positive or negative, this type of classification is termed as a binary classification. Okay. Now let's assume that we have built a model and these are the actual and predicted values. Since there are only two classes, in each of these separations you see only two boxes, spam and non-spam, spam and number of non-spams. So what this means is actually in the data there were 900 spam labels and there were 9100 non-spam labels, but the model predicted 700 spam emails and 9300 non-spam emails. So you see the difference, right, between 9100 and 9300 versus 900 and 700. This is where the confusion arises. And how is that confusion solved? Using a confusion matrix. So the same confusion matrix I've just put in the numbers. Spam is our primary class, that is first one class, positive class. Non-spam is our 0 class and also known as the negative class. We have two classes, hence a binary classification. On the x axis we have the predicted values of the model and on the y axis we have the actuals. So now let's understand using the case study, that is spam versus not spam, what are the exact meanings of true positive, true negative, false positive and false negatives. The first thing is true positives. Emails that are actually spam and the model correctly predicted them as spam. So in our example, as we saw earlier, there were 900 spam emails actually, and the model here correctly identified 600 of them as spam. Of the 900 total actual spam emails, model predicted 600 of them as spam. So that becomes our true positive. Coming to true negatives. Emails that are not spam and the model correctly predicts them as not spam. They were a class 0 and the model predicted them as class 0. So in our example, there were 9100 non-spam emails and the model correctly identifies 9000 of them as not spam. So our true negative number becomes as 9000. How to visualize this? The actual is a non-spam and the predicted is also non-spam. So the intersection becomes a true negative. Coming to false positives. Emails that are not spam. Actually, they are not spam, but the model incorrectly predicts them as spam. They are class 0, but they are predicted as class 1s, hence false positives. So in our example, there are around 9100 non-spam emails, but the model incorrectly identifies 100 of them as spam. So our false positive becomes 100. Here is our false positive. How to visualize this? In the similar way. Actually, the emails were non-spam, but the model predicted them as spam. The intersection becomes false positive. Now coming to the last one, that is false negatives. Emails that are actually spam, but the model incorrectly predicted them as not spam. That is, they were class 1 but got predicted as class 0. Hence the name false negative. There were 900 spam emails in our example use case, and the model incorrectly identifies 300 of them as a not spam. Our false negative becomes 300. So this is our false negative. How to visualize this? Actually, the email was a spam, that is a positive class, but it got predicted as a non-spam. Sorry, it got predicted as a non-spam, so intersection becomes false negative. So this is a clear definition of what confusion matrix is, and now you understand why confusion matrix is called confusion, because we are comparing actual versus predicted, and they are never, most of the times they are never the same, hence the name confusion matrix.